little bit of a review and overview. So last lecture, you had a look at voltage, the concepts of voltage, current, and power, and how we use those in electrical circuits. You heard about something called Telgen's theorem, and we introduced the concepts of DC and AC electrical currents. So a DC current is a current that does not fluctuate or change with time. An AC current is something that would fluctuate, usually sinusoidally, and change with time. Today, we're going to just firstly test those concepts a little bit, just to make sure that you're keeping up to date. And then we're going to talk about the first, maybe the second basic circuit element, which is a resistor. So the first ones that you've learnt of are voltages and current sources. Today we're going to introduce resistor. Many of you may have done this in high school. That's okay. We'll give it a quick refresher. And we're going to introduce the concept of what linear and non-linear means in terms of real-world components and how they behave. And around all this, we'll just do a few problems just to solidify all these concepts. Okay, so first up, hop on melts. Let's make sure everyone can get on. Make sure you can. I saw a question yesterday in the melts that how do you keep up to date with how many questions you've answered? So what I did was when you log into the screen, you should now see above in the unit, once you've entered the unit, there should be a little line that tells you what your score is. That's like how many correct answers you got and how many questions you've actually attempted. So note that not all questions had correct answers. So they include the questions we asked in the first lecture. So don't worry about those. Such as where was Jamie in the picture and all those. Those didn't have any correct answers. Well, I got rid of those anyway. Okay, so from your learnings yesterday, I'll give you guys a couple of minutes to get started. Determine the power absorbed and supplied by the elements in this network. Okay, so I'll just hop on melts and get that started up. Okay, and you guys can put those answers in. Oops, not that one. My password is not 1234. Okay. Oh, what is this? All right, view units. Eng1030. Oh, and also, I don't know if any of you guys have checked it out, but there is a leaderboard in here. Your nicknames, if you haven't looked into the leaderboard, you wouldn't have seen that you can change your nickname. Currently, everyone's anonymous. But people can come up with some interesting nicknames. We can have a laugh through the semester, see how everyone's going. All right, so question today. All right, have a go. So from this, what is the power absorbed or supplied by the elements in the network? So remember, we talked about the passive sign convention yesterday. Did we talk about this passive sign convention yesterday? Did Jamie? Yes, okay, good. So by the passive sign convention, positive power means that that's power absorbed. Okay, so for the sake of this question, let's make it more technically correct. Let's say, what is the power absorbed by the passive sign conventions by these three elements? 1, 2, and the source. Now, remember Telgen's theorem? That says that all the elements that generate power, well, the power generated by elements that generate power must be equal to the sum of all the elements that absorb power. Yep, question? Oh, it's locked, sorry, thank you. Yes, you're right. Okay, better? Oh, here we go. Everyone's like, give me that. Everyone's tapping on their phones. It's good, this is. All right, so let's have a look. All right, what do we got? Okay. People holding steadfastly to A. Very good. Or is it C? All right. All right. 5 more seconds. 5, 4. Anyone switching? Are we going with the crowd? Okay. So I've locked it. Okay, so very good. The crowd wins. Crowdthink wins this time. The answer is, in fact, 12 watts, 36 watts, and minus 48 watts respectively. Okay, so I think everyone's got a pretty good handle on that. Okay, so remember that the way that the arrow of the current enters into a terminal affects whether you calculate or how you calculate the power. So if current goes into the positive terminal, then by the passive sign convention you multiply those two values. So this would be 2 amps times 6 volts equals 12 watts, and that would be absorbed. Okay. Over here, the current is still 2 amps because there's nowhere else for current to go except through the elements because we've only got one circuit. And this is entering the positive terminal, so therefore the power is equal to 2 amps times 18 volts, which is equal to 36 watts absorbed, okay, because we're talking about the passive sign convention that says if the current enters the positive terminal and those values are positive, then when you multiply them together, that's absorbed power. And over here, you've got this 2 amps entering the negative terminal of the voltage source. Okay, so therefore the power is equal to the negative, and then because it's entering the negative terminal, there's a negative sign in front of your calculation, 2 times 24 volts. 2 amps times 24 volts, which is equal to negative 48 watts. Okay, and you can check this is correct because this is power supplied. Okay, and these two are power absorbed, so the sum of the power supplied must equal to the sum of the power absorbed. So when you sum them all together, total power must be 0. That's Vitelgen's theorem. Okay, very good. Okay, so moving on. Any questions about that, straight up? Hopefully, if you didn't get that at first, hopefully the explanation helps you. If not, turn to your neighbour and give him a jab in the ribs, say, hey, what the hell is he talking about? That's perfectly acceptable. Okay, so right now we're treating, as you can see in this slide, we're treating circuit elements as just black boxes. Okay, and they have an input and an output, and they're completely defined by the current that goes through the element and the voltage that goes across it. Now, that's how we like to start off, telling you, okay, you've got these things which you put together and you get currents flowing through them and you can measure voltages across them. Now we're starting to expand on that, and we're going to classify these elements into 2 types of elements, what we call active elements and what we call passive elements. And as you might guess by the name, an active element is capable of generating energy. So it might be a battery, a solar cell. You might model an active element being like a wind turbine, or it could be a turbine caused by nuclear power generation. Anything that is capable of generating energy is an active element. Then we've also got passive elements. Now these elements, as the name suggests, are passive, and they cannot generate energy. All they do is dissipate or store energy. And these are things like resistors or your friendly globes, your light globes that you put into your ceilings. So those are just 2 examples. When we're looking at, so now covering the types of active sources. So we've now got active elements and passive elements. We can further divide these into types of active elements. So here's we'll have a look at 2 of these. So one of these is independent sources. So these are active elements, and we call them independent. The reason they're independent is that the value of the source is, so here we've got a voltage source given by a circle. So the circle means that this source is independent. So that's what the circle means. And what you have inside the source defines exactly what type of source it is. So if it's got a plus minus, it means this is a voltage source. If it's got an arrow in it, it means it's a current source. Okay, so these things are great for circuit analysis because they're really easy to work with. So if you've got an independent voltage source that gives out 5 volts, for instance, then for all intents and purposes, that's all you need to know. It gives out 5 volts all the time, regardless of the current going through it. So in the real world, this is not the case. This is just an ideal case. So in the real world, you would get something like this. If my you would get the characteristic not just being a straight line across here, so you can get infinite current coming out of a voltage source. That's absolutely not true in the real world. But for circuit analysis, this is what we assume for an ideal independent source. And similarly for current, this current source will maintain a steady however many amps it's rated at, regardless of the amount of voltage that you require out of it. So these are independent active sources. Okay, so here's an example. So would we classify a car battery as a voltage source? So by our definitions, a battery can generate energy, so it's active. It's a source of voltage. So you might say, yeah, okay, cool. It is a voltage source. And if we're working with an idealized world, then okay, your battery can act as a voltage source, ideal voltage source, up to a certain point. And this is the same, this is what I can't emphasize enough. This all works mathematically and ideally up to a certain point. So when you go and turn the key in the ignition of your car, so who drives here? Yeah, most people. Who's ever had a flat battery? Yeah, okay. Who notices when your battery's getting a little bit lower in voltage and current? Well, you wouldn't know it's voltage and current, but sometimes when you turn the battery, your radio turns itself off, your lights dim, all that sort of thing, yeah? Okay, so that's because what we're trying to do is we're trying to ask this voltage source to supply us with 12 volts while we start the ignition, and we're simultaneously trying to grab a whole load of current out of that voltage source. Now, if this was an ideal source, that's all well and good. The battery will be able to do that. But in reality, a battery cannot do that. It can't maintain the voltage that you want at the same time as drawing 5 amps of current, for example. Okay, so that's the difference between real and ideal. So you've always got to keep that in mind when we're working with electric circuits, because you'll design a circuit and then you'll go, okay, cool, it works. I'm just going to now build it. But then you put your battery on, you've got the wrong type of battery maybe, and the circuit doesn't behave exactly as you want it to. Okay, so did you have a student demonstration on Tuesday of some sort? What happened there? I can't remember. Someone jumped off a table. Okay. All right. OH&S issues. That's all right. Okay. So for this student demonstration, I want to demonstrate what a dependent source is. So we've gone through independent sources, but let's go through let's illustrate what dependent source is. I can see people are shying away. Okay. People sitting next to aisles have a greater chance of being picked. So let's grab someone who's not looking at me. Everyone's looking. All right, how about you? One? Yep. Sorry, what's your name? Bryce. Yep. Come down, Bryce. And someone else as well. So strength in numbers, right? How about you? You're close. So, all right. So what's your name? Jennifer. All right, Jennifer and Bryce. Okay, so come over here. Okay, so what I want, let me turn this off. so imagine that I am current. I am flowing through a circuit. All right, so yeah, let's see. Yeah. I'm flowing through a circuit. These guys are dependent sources. All right. Supposed to do it twice, guys. All right, all right. So these guys are dependent sources, and what they do totally depends on what I do. So their value of multiplication is twice is a value of 2, so hence they're doing it twice. You get the idea, right? Okay, thanks, guys. Clap for Bryce and Jennifer. Okay, so that illustrates pretty much what we have next as a class of sources, and they are what we call dependent sources. Okay, so the difference between dependent sources and independent sources is basically, well, on a circuit diagram is you'll see that the box, well, the symbol is a diamond. It's not a circle. So that's the first indicator that this source is dependent on another value within the circuit. So whatever the voltage or current is of this source absolutely is determined by another voltage or current in the circuit. Now, if you ever think about it, you've got a voltage source and a current source, which could be either controlled by a voltage or current in the circuit. So there are 4 types of dependent sources. Where do we use these? These are largely used to model different circuit components. So we've got really easy circuit components in Eng1030, but if you stick with electrical, then you'll be looking into more and more useful little circuits that serve specific purposes. And a lot of those circuits have dependent sources in them to help model some kind of behavior. So this models an amplifier. This models what we call a transistor. Okay, so here are the 4 types of dependent sources. So over here, we've got, so we know it's dependent because there's a diamond. Oops, sorry. There's a diamond for the symbol. What kind of source is this? Is it a voltage or a current source? It's a voltage source because we've got plus minus in there. And over here, it says over here, this voltage, the output voltage, is equal to some factor, mu, times the voltage Vs in the circuit. So Vs must be defined somewhere in the circuit, and the value of V is equal to mu times Vs. So in our demonstration, mu would have been 2, because Bryce and Jennifer were copying my actions twice. And this can be any value, pretty much. And that depends on what you construct out of it. So as you might guess, over here, so this is called a voltage-controlled voltage source. I'm guessing you can figure out what these are called. So over here, you've got a voltage source, and it's controlled by a quantity Is, which is a current, right? So what would you call this? CCVS, current-controlled voltage source. And you can work through here and you can say that this is a voltage-controlled current source, and this is a current-controlled current source. Right? So the only thing I think to note in here are that you've got 2 parameters, mu and beta. So that's for this one and this one. These are dimensionless constants, because as you can see, when you multiply, you've got to make sure that the units on the left-hand side, which is in this case amps, must equal to the units on the right-hand side, which in this case is amps times beta. So in this case, beta must be dimensionless. Something that is really important, but maybe not always obvious. And R and G in this case, they're not dimensionless, okay? Because over here, you've got a voltage on the left-hand side. You've got a current on the right-hand side. So there must be some value that relates voltage to current with R here, because if not, the units wouldn't match. Okay? So the units of that must be I over V. V over I. That must be the dimension of R, and G must be the dimensions of current over voltage. Okay, so here's an example. So given our two networks shown here, what are our outputs? So the outputs here are VO, and over here the output is IO. So we've got a voltage-controlled voltage source, and the value of the output voltage VO is equal to 20 times Vs. So VO must be equal to 20 Vs, which must be equal to 20 times 2 equals 40 volts. Okay, so that's fairly simple. Here's another one. So IO here must be equal to 50 Is, and this must be equal to 50 times 1 milliamp, which is equal to 50 milliamps. All happy with that? Okay. So now here's our next melts example. So this will take a couple of minutes for you. And it's basically, you've got it in your notes if you printed them out. Work out what IO is using Teldrin's theorem. Okay, so have a go. So remember Teldrin's theorem? Work out all the powers that each element is absorbing or supplying. So to do that, make sure you're multiplying. If the current is going into the positive terminal, then you multiply the two values together, and if it's positive, it's absorbing. If the current goes into the negative terminal, then you have to add a negative sign in front of it. So using that, find I0 in the network. Let me just check the next slide. Yeah, so here's the slide. So I'll give you a couple of minutes to have a look at that. Turn to your partners. There's absolutely nothing wrong with doing this in groups and having a go. You can talk. Talk is good. It means people are figuring things out. If you think your friend is wrong, jump up and point at them or something, I don't know. So you'll probably find this looks a bit like a puzzle. You'll probably find most of circuit analysis is like a puzzle. It's really finding the parts you don't have from all the parts you do have. Okay, so I'll help you out. So you keep working on it, but I'll help you out with some calculations. So this is for okay, so last chance. Quickly press anything. What do people press when they randomly have to press something? It's interesting to see. People are randomly pressing B, okay. Or none of the above, okay. All right, 5, 4, 3, 2, 1. And what do we have? The answer is, where's my melts window? There it is. The answer is A. Okay, so this is a good test of your understanding of calculating power, the way that current is going into and out of these elements, which have plus and minus signs everywhere. It's testing whether you understand how all the power summed comes to a particular number. And we come up with 1 amp, which is correct. Very good. Give yourself a mental or literal pat on the back. Can you reach back and pat your back? Nobody wants to pat their back? Oh, come on. Boo. All right. Okay, so we okay with that? So what we do is from here, you sum up all the negative powers supplied by all the elements that are supplying. You sum up the elements which we believe are absorbing. You come up with an equation, and you can figure out that I0 is equal to 1 amp. Incidentally, you'll learn next Monday that there's a really, really easier way of doing this. Of course, we want to make it seem difficult. No, the really easy way is you'll learn something called Kirchhoff's current law. Right? And what this says is that if you look at any interconnection point between elements, then the sum of the currents must be equal to 0, as in the sum of all the currents coming in must be equal to 0, or the sum of all the currents going out must be 0. So what that says here is that if we look at I0 and you look at the current coming into this, what we call node, you've got 3 amps here and you've got 2 amps coming out here. Well, simply this must mean that this must be 1 amp when we sum them all together. All right, so sorry to make you do all that, but that'll come apparent next week. Okay, but the key thing here is that what Teldrum's theorem says is that we obey the most fundamental physical law of conservation of energy. Yes? Yes? So you've got the current here, 11 amps, and this value, because it's a voltage source, right? This value must be in a unit which is not dimensionless. Yeah? Yep, so it's 8, in fact it's actually 8 ohms it would be. This unit of this constant would be in ohms, it's not dimensionless. So that's why it becomes a voltage. Very good spot though. Yes, nobody's ever spotted that one before. Good on you. Okay. Okay, so now let's move on to resistors. Where do resistors come from? There's this dude called Ohm who basically took batteries that were produced by a dude called Volta. Imagine that. And what he did is he experimented with these. He basically put wires on them and different materials, and he tried to measure what the voltage and the current relationship was depending on what kind of conductor he put across it. And he found that different conductors had different relationships and different relationships between the voltage and the current when I put something across there. So this thing he basically gave the name of what we call a resistor, and it's measured in ohms. Okay, so this was measured in ohms. And so this says that if you've got a current going in here and you've got a voltage across it, that there's a relationship between the voltage and the current which is dictated by what we call Ohm's law. Okay? That's a whole load of words which can be summarized in a picture. Okay, so it says that if I have some sort of device, now we're introducing this new device, which you've probably seen before, called a resistor. So now we're not just looking at these black boxes anymore. All right, this is a resistor, and it's given by a squiggly line. Okay. Note the squiggle is actually like a sawtooth. It's like a saw. Okay, as opposed to something. So if you squiggle this, it actually means something different to squiggling this. So be careful when you squiggle your diagrams. And we do come across this later in the semester. Okay, so be careful how you draw a resistor. So basically it says, if I have an element which behaves like this, it's called a resistor, and how it behaves is that if I plot the voltage measured across the resistor against the current that flows through the resistor, it obeys a linear law with a proportionality constant, which we designate as R. Okay, and R for a resistor is what we call its resistance. Okay, and it's measured in ohms, and this is the symbol for ohms. It's an omega symbol in Greek, and 1 ohm is equal to 1 volt over 1 amp. Okay, so that's why in this previous slide, this 8 would be in ohms, because that's equal to volt over amp. This one is an amp, is in amps, and this one is in volts. So and the other side is in volt amps, because power is measured in volt amps. So when you multiply all this out, you should get volt amps. That's why those constants matter. Okay, now anyone got a friend or family who's got a birthday coming up? Yes? Yes? Yeah, you have a friend or family? Okay, so yeah, so we've got ideas for gifts, perfect gifts, which are electrical engineering related. How about this for a t-shirt that you can wear around? Resistance is futile, basically bow to me, if less than 1 ohm. So there's a slight caveat there. Another gift, resistor, but voltage is totally awesome, right? Okay, so these are gifts which might be good for guys. We've got gifts which might be good for girls shortly. But here's what resistors look like. Okay, so here are examples of resistors. This is the most common one. You'll run into this in your labs. You'll be given these users. These ones are created using silicon, and they're fabricated onto boards. And here are some other bigger resistors which can hold This is actually a heat sink that sits around this resistor because this resistor can get really hot. Okay, and why? So I've told you on one hand that the VI relationship for a resistor is linear up to a certain point. So just like voltage sources and current sources behave well and ideally up to a certain point, so do resistors. In fact, in the real world, resistors behave a bit more like this. So if I put a whole load of current to a resistor, then its voltage, like if we get into really big values, we start running into, say, this region of positive current or negative current, so current in either direction. Then the voltage relationship with the current starts to go non-linear. Okay? Just to be aware of this when we're designing circuits, so you don't go, hey, I want to build something which gives me current, and I want to put 50,000 volts across this small resistor. Why is my current not, correspondingly large? And it's because you've got real-world factors coming in place. Resistors actually explode and stuff if you do bad things to them. So what's a power in a resistor? So remember that power we calculate for any circuit element. The power across that element is, so here's a circuit element, here's voltage, and here's the current. We said that the power was equal to VI, which you've practiced now a couple of times, which is good. Well, it's exactly the same for a resistor. However, we also know, so this is the power, we also know that the voltage is equal to this proportionality constant, R, times the current. So we've got two equations now. We can combine these, so we can actually take this and plug it into here, do a little bit of algebraic manipulation, and you can find the power for any resistor. Only a resistor can be this simplified version, which is R times the square of the current, or the square of the voltage divided by R. They're both equivalent. Yep, is that a question, or is that a stretch? I'm stretching too. Sorry. Okay. Now, what this says is that if I put a really large current through a resistor, right, I'm going to square that current and multiply it by its resistance to give me the power. So bigger currents will mean that the resistor is absorbing more power, as does larger voltages, but the resistance actually lowers the power with respect to the square of the voltage. So there is a limit to, now what happens where does all that power go in a resistor? So you're dumping a whole lot of current in a resistor, what happens to it? Heat, right? So resistors get hot. So if you pump a whole lot of current through a resistor, don't go touching it because it will be hot. Okay, so just before, I've got a little video, but here's a perfect gift, part 2. So this is for all the ladies. So we've got resistor-made jewelry. Yeah, so here's some ideas for your next gift. And how about some circuit high heels? What do you reckon about that, eh? Could be slight OH&S hazard. Could be quite painful for anyone you kick. But yeah, there's some ideas for you. Okay, so where's that video that I had? Anyway, I had a cool video of an exploding resistor. It should be here. Let me check. Ah, here it is. Do you want to see the video first or do the problem first? Yeah, video, of course. All right. Okay, so here we go. It's only like the cool stuff is there. Okay, so here's someone chucking 20 amps through this resistor. Oop, there it goes. So yeah, you're like, yeah, whatever. That's fine. All right, so here he's getting more. Ooh, there we go. Yeah, the guy's pretty happy with himself. Okay, so this is a really high valued resistor. So it's like in the mega ohms resistance, and he's putting, yeah, so this one's a bit more of a slow burn. Yeah, it's getting pretty hot. I wouldn't be touching it. It's getting really seriously smoky now. You'll set off the fire alarms in the labs. Don't do it. And here we go. Yeah, so this can basically happen if you get, so you know how we always say short circuits are bad, okay? So if you plug in something into your, if you get a short circuit in one of your circuits which takes a current from the loop from the mains, you might be getting like tens of amps through your electrical hardware. If your electrical hardware has resistors in them and they're passing through lots and lots of current, then this can happen. And if this happens more seriously, you can start fires and stuff, which does happen with poorly designed electrical circuits. Okay, so cool, but also dangerous. Okay, so let's have a look. So here's a quick example. So let's say you've got a 100 ohm resistor. So R equals 100 ohms. Connected to a 5 volt power supply. So V equals 5 volts. So what does that look like? So you've got plus minus 5 volts here. And we're connecting that directly to a resistor of 100 ohms. Then how much current flows through the resistor? So here you've got 5 volts. And you've got current coming this way. So what is I equal to? Is the question. So how do we find what the current is that flows through the resistor? Well, we know from Ohm's law that V equals IR. Now, what we're saying here is that the voltage and the current are measured using the passive sign convention. So if the current is flowing in... Now, the cool thing about resistors is you don't really need to... whatever terminal it goes into is always going to be... This thing is always going to be absorbing energy. It's a passive component that always absorbs energy. The way that the voltage pans out across this loop is that you'll get 5 volts with current coming into the positive terminal. So this gives us 5 volts equals to the current times our resistance. And so the current becomes equal to 5 over 100. So that's 5 volts over 100 amps, which gives us 0.05, 100 ohms, which gives us 0.05 amps. Okay? Now, given this, what power is absorbed by the resistor? So we said power is equal to either equal to I squared R or V squared on R. Probably easier just to use V squared on R because we've got here. So it's 5 squared over 100 ohms. And the power would be 25 divided by 100, which is equal to 0.25 watts. So this is the amount of power that this resistor is absorbing when we put a 5 volt, when we connect a 5 volt source to it. If we connected a 240 volt source, then you would get a corresponding increase in power. Well, you'd get the 240 squared divided by 100. You'd get a lot bigger amount of power being absorbed. So what does this part of this question mean? So this says a metal film resistor has a power rating of 0.25 watts. So what is a power rating, you ask? A power rating is basically the amount of power that a resistor can absorb without getting destroyed. Okay? So in the previous example, or well, on the video, that would have had a corresponding power rating, and obviously because we put too much current and voltage across it, that exceeded the power rating of the resistor, and the resistor died, basically. Okay, so in that case, just do this one, just really quickly. I'll give you 1 minute. You've got the slides there. Where is my Chrome? Here we go. I'll give you 1 minute to do that. You've got that in your notes, I believe. What is the current flowing through, and will it be okay? Okay, so you've got 15 ohm resistor. So I've got a resistor here, 15 ohms. And I've connected it to a 12 volt source. What is the current? And what is the power? And this is a similar resistor before, so its power rating was 0.25 watts. Will this resistor survive, is the question. Okay, so how do we calculate the current? So we know that V equals 12 volts, R equals 15 ohms. So therefore, the current V equals IR is Ohm's law, and therefore I equals V on R, which is equal to 12 over 15, which is equal to 0.8 amps. Okay, so that's the current. How are people going with that? Yep, good. And you can all, I can see that you can all realize that the power will be equal to V squared, which is 144 over 15, whatever value that is, so it's like 9.6 watts. All right. And so will this resistor be okay, or has it gone to resistor heaven? It's gone to resistor heaven, right? It's gone pff, just like the other one. Okay. Very good. Okay, now finally, there are some important values of resistance that correspond to how we wire up a circuit. Okay, so over here, if I have a look at this, if I have a short circuit, that corresponds to a wire connected across a voltage source, and in this case, the resistance will be equal to 0. So ideally, we say that any piece of wire has 0 resistance. Okay? Now, in reality, this is not the case because wires do have resistance. If we have an open circuit, which is what this is called, the resistance across these two terminals, so if I connected an imaginary resistor, so this is an imaginary resistor, this resistor would be equal to infinity. Whoops, not 8. You've got to turn your head sideways. It'd be equal to infinity if I have an open circuit with nothing connected across it. Okay, and finally, sometimes, if we've got really low values of resistance, so if our resistance is like 0.001 ohms, it makes more sense to talk about what we call the conductance of the circuit. And the conductance is basically the reciprocal of the resistance. So you've got G being 1 over R, and the units of conductance is what we call a Siemens or a mho. Mho. Okay, so that's it for today. We do have a couple of questions which you can attempt in your own time. Oh, and finally, why did Mr. Ohm marry Mrs. Ohm? Because he couldn't resist her. All right, thanks very much. See you next week.